Hey everyone, welcome to the last video from section 2.4, which really isn't about 2.4, it's about section 2.8, but I'm calling it 2.4 because that's kind of where it fits. The section's about the existence and uniqueness theorems, and it goes more into the proofs and sort of structure of the actual theorem itself. There's not too much in here that's really necessary for this class. There's a lot of more advanced math stuff going on here. So what I'm going to do is I'm going to go kind of give a vague idea about this section, what's going on in there, and then we'll just kind of move on from there. I'll give you a vague idea, set up what's going on, and then we'll go on to more practical things. All right, let's go ahead and jump on into that. So in this section in 2.8, we're looking to solve the nonlinear equation, y prime equals f of ty, and we're going to assume we have the initial condition y of 0 equals 0. You can get away without this, but we're just going to put it there for convenience sake. It's nothing too big of a deal, it's just kind of there. So what we want to do to sort of get a handle on this is we want to write this equation in a different form. So what we're going to do is we're going to assume we have a solution. So we'll assume that phi of t solves this, which means what? It means phi prime of t equals f of t phi of t. That is what it means for a function to be a solution of that ODE. Now what I want to do is I want to apply the fundamental theorem of calculus to write this in a slightly different form. So Calc 1 fundamental theorem of calculus tells me I can write phi of t minus phi of 0 as the integral from 0 to t phi prime of s ds. Now, I know what phi prime of s is because I have the equation directly above that one. So I can replace that by the function f. So this equals the integral from 0 to t f of s phi of s ds. And on the far left of the equation, I know phi of 0 is 0 because phi satisfies the initial condition. So this just becomes over here a phi of t. So putting just the far left and the far right together, I get what's called an integral equation for phi. Phi of t equals integral 0 to t f of s phi of s ds. Now, this has gotten us no closer to actually solving the problem. None at all. We've just rewritten the problem in a different form. So I guess the question to be asking is, well, why do we do this? Why do we even care about this? What's this form do us any better that it didn't do before? And the main thing here is that we don't have any derivatives anymore. There is just phi on the left and phi on the right. There is no phi prime anymore. And that's what's going to end up helping us out. So the way we utilize this formulation to say the solution to the problem exists is via the method of successive approximations. It's also called Picard iteration. Not Jean-Luc, unfortunately, but Picard iteration nonetheless. So the idea of this is we're going to iterate something and result in a solution to the equation. So let's take any function phi1. I don't care what it is, just pick a function phi1. It better be at least continuous, but take any function phi1 of t. And now from this phi1, I'm going to generate a phi2. I'm going to set phi2 of t to be the integral from 0 to t f of s phi1 of s ds. So from phi1, I can get phi2, and then we're going to keep repeating this. So I'm going to get phi3 of t is integral 0 to t f of s phi2 of s ds, and then we're just going to keep on going. So I can do this as many times as I want. So I get a sequence where phi n plus 1 of t is the integral from 0 to t of f of s phi n of s ds. And that builds me a sequence of functions. Now, what you want to end up proving is that this sequence converges somehow. So if it converges in a nice enough way, then this is going to converge to some function phi of t. We're assuming it'll converge to that. But now what happens to the right-hand side? Well, the right-hand side stays integral 0 t f of s, and now if phi n plus 1 converges to some function phi n will also converge to the same function. It's just one step behind in the sequence. It's going to end up converging to the same thing as n goes to infinity. So I will get a phi of s in here as well. And what is that? That is exactly the integral equation that we had for our ODE. So if we get that this converges, then we get a solution. If this phi n conversion converges nice enough so that it'll work in both the left-hand side and the right-hand side, then from this method, I get a solution to the ODE right here, to the integral equation. So that's the idea. If I can find these functions phis that do this right thing, then we're all set. And now how do you actually go about that? Well, that's where you need the assumptions of the theorem. In order for this to work, this works if f is continuous, and if the y derivative of f, where the function phis are, if that's also continuous, then this works. And you can show that there is a limit point, there is a limit, it's unique, you get your answer that way, and you get everything out of that there. How you actually do that is well beyond what we're going to cover in this course, and it's not really important to know that. The important thing, I guess, to know is that this method's out there, and it works. And there'll be problems that ask about successive approximations. I don't know if I'll ask about them on the test or not, but they exist. It's just doing this sort of approximation. But if you look at it, if f is at all complicated, this operation gets really, really nasty really fast. Because you're iterating the function f and then taking an integral, and then plugging it back into f and taking an integral. So f is anything more than just like a very, very simple expression. This gets bad very quickly. So there really isn't too much you can do computationally with this. So the idea is it's more of a theoretical argument to get you to say a solution exists and it is unique, more than a computational way to actually find a solution. All right, that's all I really want to talk about for this video and for this section. Actually, there's a lot of math in this section. If you're curious, you can look at it. If you want to talk to me about it, come let me know. But this is all I'm really going to cover for section 2.8. Thanks a lot for watching, and I will see you in the next video where we'll take on the next section, section 2.5.